Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Hi, everyone. It's a pleasure to have everyone here today. We have the tough post-lunch spot, so we had to make an extra terrific presentation for you to make sure you stay awake, digest properly. I am pleased to, my name's Donald Brinkman. I'm a program manager with Microsoft Research Connections. I work in Games for Learning and Digital Humanities. And it is my pleasure to introduce this panel. We've brought together some really fabulous researchers from inside and outside of Microsoft that are all working together to find ways to use applied program synthesis and program verification technologies to solve really tough educational problems. And so I'm going to do quick introductions here and lay out the game plan for today. We have Armando Soler-Lizama. He's an associate professor without tenure at Massachusetts Institute of Technology, working on program synthesis. He's lead of the computer-aided programming group. And he's going to show how program synthesis can be applied to the problem of automatically creating feedback for programming assignments. And after him, we're going to bring in Sumit Golwani. He's a researcher in the RISE group here in MSR. And he's been working a lot in the area of program synthesis. You may be familiar with one of the products of his work, one of my favorite things to come out of MSR in recent years, which is the flash fill functionality inside of Excel 2013. And he's going to talk about program verification and synthesis technologies in the application of sort of problem generation. And then we're going to wrap this up with Zoran Popovic, who's a full professor at University of Washington. He's the director of the Center for Game Science there. Really amazing guy. You may know him for one of the folks who brought Fold It into reality several years ago. He's also the founder of Engage Learning. His tech's been licensed to many game companies, and he's been applying his work and research and some of Sumit's research to specialization technologies for maximizing engagement in students, for individual students in classrooms. So we're going to go through this fairly rapidly. These guys are going to talk. I'm asking that please let's reserve questions. If you have a burning question in the middle of the talk, just go ahead and interrupt them. But in general, if you can reserve questions for the end, and we'll do a little general Q&A for everybody. So with that, I'm going to let Armando take the stage.
All right, thank you, Donald, for the introduction, and thank you all of you for coming to the talk. So the work I'm going to present today is actually done primarily by my student Rishabh Singh in collaboration with Sumit Golwani and I. And the basic problem that we're looking at is how to provide meaningful feedback to students working on introductory programming assignments. So if you look at what happens today, there are basically two mechanisms that people use to provide this kind of feedback. The first one is to use tests. Somebody writes a test suite to evaluate the program. Some tests pass, some tests fails, and based on that, you give some feedback to the student about your program works for this, it doesn't work for that. Students don't really like it, especially at this stage. Now, the alternative approach is to actually get an army of TAs to go and stare at the student solutions for a long time and figure out what was the student thinking. What were they trying to do with this code that they wrote? Is it totally wrong? Or were they actually really close to getting to a working solution? And the problem with this, first of all, it's very expensive. Second of all, it's actually easy for the TAs to fall back on the tests and to over-rely on these tests. And then students really, really dislike it. In particular, if they feel that the feedback that they're getting is not really helping them learn, if they feel like their feedback is not really reflecting the effort and the accomplishment that they put into this code. And especially if it takes a long time, then the students really don't like it. Now, this is a problem today. It's a problem if you're teaching a course with 50 students, 100 students, but it's going to be an even bigger problem once you look at the setup of MOOCs. Because now you're no longer talking about a number of students where you can have a set of TAs look at the solutions. The set of students is too big, and you still want to give them this personalized feedback. So this is where technology comes in. This is where we want to do something about this problem. So how are we going to do that? Let's start by looking at how one might do this if you actually do have this army of TAs. So the student goes and submits a solution. One of the first things that you need to provide these TAs with in order for them to do their job is you need to tell them what the problem is. They need to have some kind of reference solution that they have so that they have an idea of what they are actually grading against. But the second thing that is very important is you actually want to give them some grading rubric. The TAs or the graders need to have some idea about what are the kind of errors they are looking for, what are the kind of mistakes that students commonly make, and actually how many points you want to deduct for different kinds of errors. And based on that, a smart TA can actually go in and tell the student, oh yeah, you are almost correct. You only made some small mistake here, some small mistake there. If you fix those, your program will work. You are pretty close. Or maybe you want to tell the student, no, you're totally in the wrong track. You need to do something different. So this is the kind of workflow that we want to automate, except instead of an army of TAs, now we actually want to have an automated system in the loop. Now, there's a few technical challenges in order to achieve these. The first one is that if you look at a given student submission, there's actually a very large space of possible corrections that one can make, possible things that might go wrong, possible errors that a student might make, and that you have to consider in order to find what the right correction is. The other thing is it's not enough to figure out some way of doing corrections. You actually want to find a minimal way of doing corrections. You want to go back to the student and say, yeah, you are really close. If you only change these 2 or 3 things in your program, things will work correctly. And finally, we actually want to do this in the context of the languages that people use, especially when teaching introductory programming. And in particular, for the courses that we've been looking at, the language of choice is Python. And that introduces its own set of issues. It's a hard language to analyze statically because of the absence of static typing information. So we have to deal with that. Now, the basic tool that we're bringing to the table is constraint-based synthesis. It's a family of approaches that we've been working on for many years as part of our work on computer-aided programming that we're actually bringing to bear into this problem. And it will become clearer how we do that in a few slides. But first, I want to give you a small example of the kind of programming exercises that we're talking about. So these are really the kind of programming exercises that you want to give students in their first programming course. They're just learning about loops. They're just learning about variables. They're just learning the basics of programming. They don't yet have the skills, for example, to debug their own code. They are learning to program. So here is a problem actually from 600, which is one of the introductory programming courses at MIT. So in this case, the problem statement is very simple. You have a function, and you're going to give this function a polynomial, represented as a list of coefficients. And the goal is to find the derivative of this polynomial. So, there's a pretty simple algorithm to do this from your grade school calculus class. But now we want to write a program that will do this for you. So this is the task that is given to all the students in this class and that they have to solve. And, some students get closer to a correct solution than others. But one of the things you want to do is you want to provide, if you're going to do automated grading, you need a reference solution. You need to know what it is that the true solution looks like. The system needs to know this in order to be able to give meaningful feedback. So in this case, this is the kind of reference solution that a teacher might write to either do any kind of testing or even to give the TA so they know what they're looking for. And now let's look at what kind of things our system can do. So here, what we actually have are some sample solutions that we got from the edX version of this course. There were several tens of thousands of students taking this course, and lots of them make mistakes when trying to solve this problem. And this is a particular solution that some students submitted. Can anybody tell me what's wrong with this solution? Probably not just by staring at it, but we can actually ask the system, and the system looks at it. It actually looks at the solution. It looks at the reference solution that the teacher provided, and then it looks at a set of correction rules and searches these exponential space of possible corrections to this program to actually come up with some feedback. So what is the system telling us here? It's telling us that in this range expression, you want to increment length by 1. So let's see, where is that expression? Line 14. So here it's actually going to go to length plus 1. And we can try this now. And let's see what it tells us. So the system, again, is looking at this problem. It's looking at the space of possible solutions. It goes in and it tells us, oh, yeah, you also need to change these operator. It can't just be greater than or equal to. If you do not equal to, it's actually going to work. One of the things you can do is you can tailor the level of feedback that you provide to the student. So at one level, you can tell the student, oh, you know what? I don't want to go and give you the solution. But all I want to tell you is that you're pretty close and that you just have one small mistake on line 19. Or I can actually go in and direct you to the exact expression that you should be looking at that actually has a problem. Or I can tell you that there's a problem with this operator, but I'm not going to tell you exactly how to fix it. Now, the cool thing about this approach is that I can give you a different solution that looks totally different from before. I can even give you a solution that uses, for example, list comprehensions. And I can go to the system and ask it, is this correct? And the system says, yeah, it's actually almost correct, but you have a small problem here. This should not just be range of length. It should actually go from 1 to length. So the system is actually figuring out how to make small corrections to these programs in order to get you a solution that behaves according to the reference implementation. You might even have some students who do some fairly involved solutions, even solutions involving, some loops and modifying the list as they go along. But the system is able to reason about that. Now, if you give it a more complex solution, the system is going to take a little bit longer to analyze it and to figure out what the actual solution is and how to actually correct this. And I think this one takes about a minute. So I'm going to go to the slide, and we can go back and see what it tells us afterwards. So this is cool. Now let's see how it actually works. How can we actually get a system to give us these kind of level of feedback? So as I said before, one of the first things we need is an error model. And in particular, by an error model, what we mean is some set of correction rules that, when applied, might be able to take your program from being incorrect to being correct. And here is a very simple error model that I'm using just for the sake of showing you how these error models look like. So your error model might say things like, oh, whenever you see a return A, instead of actually returning A, you might want to return a list containing 0, or you might want to return some other variable that's not A, some different variable. Or you can say things like, hey, whenever you see range from A1 to A2, you might want to replace that with range of A1 plus 1 to A2. Or whenever you see an equality comparison, you might just want to set that to false. So these are the kind of correction rules that are built into the system. Now, the problem is every one of these correction rules is going to potentially be applied at many different places in the program, and it's actually going to lead to an exponential search space. So this is where our algorithm comes in, and this is where synthesis comes in. So The basic strategy behind our algorithm, it's essentially a 4-phase algorithm. The first phase is we're taking these rewrite rules and we're translating the original program into a compact representation of this exponentially large space of possible programs that the student might have wanted to write. And then we're going to translate that into the input language of a sketch synthesis tool called Sketch that I'm going to talk about a little bit later on. And Sketch is actually going to figure out these optimal set of corrections, these correct program that matches your specification and that is a minimal distance away from the program that the student wrote. And now once you have that, you have to translate that into meaningful feedback for the student. So in terms of rewriting, what we're doing is, again, we're applying these rewrite rules. Now, the problem is, even a simple rewrite rule like this actually can induce a very large space of possible programs. For example, if we have an expression like this, and we have a rule that says any expression might be the expression plus 1, well, that means that when we have 0, this might actually be a 1. But we want to remember the fact that 0 is the default choice. 0 is the zero-cost choice because it involves no modification to the student program. Similarly, when we have this poly expression, the system says, well, maybe that poly expression should be poly plus 1. Now, if you had a typed language, the system would realize that there's no such thing as poly plus 1 because poly is actually a list. But remember, this is Python. There are no types. So at this point, the system has to assume that maybe poly plus 1 is a valid expression. And then the length expression itself, maybe you want the length, or maybe you want the length plus 1. So you can see how out of this very simple rule and out of this very simple expression, now we have 4 different possible expressions that the student might have wanted to write, and one of them might lead to the correct program. The other ones might lead to an incorrect program. So how do you search these giant space? And now you're actually doing that not just on one expression, but on every single expression in the program. And this is how you get exponentially large search spaces that you have to search. And the key is not to search that space explicitly, but instead to rely on logical reasoning, to do a symbolic search. So in order to understand how we do that, it's worth talking a little bit about the synthesis technology that we have been developing for quite a long time. And so I'm going to segue a little bit to give you a brief introduction to what this technology is all about. The basic synthesis problem is that you want to know whether there exists some program such that for all inputs, that program, together with that input, satisfies a specification. Now, quantifying over programs, however, is difficult. So what we're going to do instead is we're going to borrow a trick from the machine learning community, which is, instead of looking at arbitrary programs, we're going to look at parameterized families of programs. So the idea is you have this parameterized program. So now, instead of having to search over a space of programs, you're having to search over a space of parameters. So now you have this problem with this quantifier alternation that you're trying to solve. And we actually have developed this language called Sketch, which gives you a mechanism for defining these parameterized programs to make it look like you're writing essentially partial programs that the synthesizer has to compute. And this is essentially the hello world for Sketch. One of the basic things that Sketch allows you to do is to say, if I have a constant and I have some assertions, the system can go in and figure out a value of this constant that will make these assertions work correctly for all possible inputs, usually within a given input size bound. It's actually going to be doing some bounded analysis in order to check whether it has the correct thing or not. Now, once you have that language, then there are still a lot of major issues in terms of handling Python's dynamic types, in terms of how do you actually translate those expression choices into these sketches. I'm not going to talk too much about this because instead I want to tell you a little bit about the actual technology that we use. Once you actually frame the problem in this way, how do you solve for these unknowns? And the basic idea is this algorithm called counterexample guided inductive synthesis, which we developed in my group several years ago. And the basic idea is that searching for parameters, or in this case, searching for corrections that work for all possible inputs is hard. So instead, you want to look for corrections that work for carefully crafted inputs. And the idea is once you find some set of corrections that works for that carefully crafted set of inputs, you can actually check them using standard off-the-shelf checking technologies such as automated test generation and bounded model checking in order to check whether this is actually correct. So the idea is you have this initial constraint that you're trying to satisfy, and you start with some random input. And so you rule out all the set of corrections that will not work even for that random input. So you find some set of corrections that works for that random input. If it turns out that that set of corrections doesn't work in general, then this kind of automated checking technology can give you a counterexample. And you can keep doing this until the process converges. Every time you get a new counterexample, you're eliminating an exponential set of possible corrections until you get to the solution that you actually want, the solution that actually satisfies your specification. And using that algorithm, we're actually able to find this feedback in a matter of seconds, as I showed you in the demo. And once you find what the correction is, once you find what the problem is, then it's really just a matter of filling out the template in order to give the English language version of these feedback. So does this work? So in order to test this, we looked at a few primary sources of problems. One was the 600 course from MIT, both the MIT and the edX version, as well as some data we had from PECs for Fun. And we're looking primarily at programs dealing with integers, Boolean, strings, lists, dictionaries, tuples. We can't handle classes yet. We're actually working on support for that. But we have a large set of problems, again, primarily from these two courses. For some of them, we have small numbers of assignments coming from students taking the actual course. For others, we actually have several thousands of assignments that came from the edX version of the course, corresponding to those incorrect solutions on which the students were not able to fix them. So what you find is that the average running time is actually not that high. For some problems, it's a little bit longer than others. But in general, we're working with cutoff times on the order of 3 minutes. So most of these, there are some problems. There's a handful of problems that take longer. But by and large, a lot of the ones that don't time out work pretty well. Now, what you can see is that there's a set of problems that actually work really well for this approach. But there are also some problems for which finding minimal corrections doesn't quite allow you to correct large percentages of errors. And the primary reason for that is, a small number of them have to do with students just going crazy and using crazy Python features, or writing things like completely empty bodies, which obviously you cannot fix just by local rewrite rules. A handful of them are timeouts, but the most interesting set are cases where the students are making big conceptual errors. For example, one big conceptual error that is very common is the student might have a major misunderstanding about how an API works. For example, in the case of this student thought that the index function would tell you the index of element I. But in fact, the index function tells you the index of the first element equal to I. So if your list has repeated elements, this will give you the wrong answer. And there's no small set of corrections that you can make on this to give you the right answer. The student simply has the wrong idea on how to solve the problem because of a misunderstanding of how this works. Here's another instance where, as part of an implementation of the hangman problem, the student has to take a secret word and replace letters that have not been guessed with underscores. But in this case, the student is replacing letters that have been guessed with the underscore. So the student is misunderstanding the specification of the function, and therefore is giving the right answer to the wrong problem. And you can't fix this just by local rules. You really want to alert the student that they're solving the wrong problem. So this is the basic technique that we have. And one of the big things that we're interested in is moving beyond just giving feedback to actual active tutoring of the students to help them confront their misunderstandings, particularly when it comes to these big conceptual errors. And if you want to know more, actually send us email. This is my student's email, and he's always eager to get email. So thank you very much.
All right, thank you. Yeah, Sumit's up next. Gosh, it's hard when we don't have feedback monitors. I'm like watching TV without a screen. But Sumit's going to talk about generating problems, which is something we all need more of.
Not generating research problems, right?
Okay, hello everyone. So I'm going to be talking about automated problem generation for a variety of different subject domains. And this is joint work with several collaborators, and you will see their names pop up when I talk about that specific topic. So there might be several motivations that different teachers might have in order to be able to use a technology for automatically generating problems. Sometimes you might want to generate problems that are similar to a given problem that a teacher might have access to. And this might be useful because that original problem might come from a copyrighted source, but then you can use our technology to generate problems which are not exactly the same as that one, but are similar to that one. So this might be a little bit of a debatable issue, though. Another reason for generating similar problems is that every student in the class can get a different version of the problem. So this can help prevent plagiarism. And this is especially important in MOOCs, where you might want to have some kind of unsynchronized instruction going on. Then you might also want to generate problems that have a given difficulty level and that exercise uses of certain concepts. And this can be useful because you can use this technology to help generate a progression of problems that start from simple and become more difficult and involve more sophisticated concepts. And this can also be used to generate personalized workflows for students. So different students might be understanding the subject content at their own pace. And if a student solves a problem correctly, you might want to take them to a problem which is more difficult or that involves different concepts, and vice versa. So I'm going to be talking about problem generation for a variety of subject domains. This ranges from arithmetic, algebra, logic, even language learning, board games. But the techniques that we have used for each of these different subject domains may be generalized to some other similar subject domains as well. And in order for you to be able to appreciate these things, I have tried to come up with a classification of these different subject domains. So I would like to classify them into two categories, procedural and conceptual. So by procedural, I mean, one of the good examples for a procedural category is mathematical procedures that students learn in middle school mathematics. So here the student is supposed to memorize a given procedure and they demonstrate that procedure on a specific input. So for example, students are asked to add large numbers, multiply them, compute GCD, LCM, and so on. So they have a specific procedure that the teacher has taught them, and the student is supposed to demonstrate this procedure on some given inputs. Now, the procedural learning is not just restricted to middle school mathematics. You often also see them in undergraduate curriculum. So for example, in an introductory algorithms course, the student might be expected to understand how a specific algorithm works, such as Dijkstra's shortest path algorithm, and then be able to demonstrate their understanding on a given graph. Then the second kind of subject domains is what I call conceptual. So here there is no specific procedure or decision procedure that a student can memorize and solve these kinds of problems. But a student really has to do some kind of creative thinking and find some patterns in the problem. This can include proof problems, like in proving algebraic theorems, or doing logic proofs in natural deduction, or proving that a certain language is non-regular. Or this can also include doing some constructions, like geometric ruler compass-based constructions, constructing an automata, or constructing a new algorithm. So these are some of the ideas that we have used for building automated problem generation tools for a variety of subject domains. And I'm going to highlight one of the key ideas, which is inspired by work on program verification or program testing. So at Microsoft, we have invested into decades of research for building tools that can find bugs in software. And now what I'm going to show you is how we can use this technology pretty much in a black box manner for helping generate problems for procedural content. So let's start out by a problem area from middle school mathematics, which is how to add two long numbers. So if you were to teach someone how to add two numbers, you might want to go about teaching the different concepts involved in this particular problem. So I will start out by teaching the student how to add single-digit numbers, then maybe multiple-digit numbers without carry. Then I will go on to teaching how to add numbers with a single carry, then maybe double carry, triple carry, and so on. So these are the concepts that I have listed down that start from easy to more difficult. So now I'm going to tell you an automated procedure to be able to generate problems that will exercise these concepts in this order of difficulty. So I've written down a program that performs addition of two numbers just as a student is expected to add two numbers. So note that I didn't write a plus b, right? But what I've really written down is I've captured the two inputs as an array of digits, and I'm going to be adding them from right to left. And this is a program that does it by maintaining carries and so on. Then I've also provided labels on the right side of this program. Now these different concepts that I've shown you, they really correspond to different traces in this program, which I've captured by means of these regular expressions that you see in the second column. And now we can use test case input generation technology, which has typically been applied to find bugs in programs, to be able to explore these different paths that are specified by this regular expression. And you get an automated tool to be able to generate problems that exercise different concepts for a given procedural problem. So the recipe is as simple as writing down the procedure that the student is supposed to master, and then use test case input generation tools to be able to generate inputs that will explore different paths in this procedure, because these different paths in order of difficulty actually capture different concepts. So this is joint work with Zoran Popovic, who will be talking about this technology in more detail, and his PhD student Eric Anderson. So we have also used this technology for doing one other fun thing, which is to compare progressions of problems from two different textbooks. So in this case, this is a procedure that compares two integers, which integer is larger. So the first part of this procedure simply checks the number of digits in the two numbers. If one number has a larger number of digits, then that number is going to be larger than the other one. And if not, then it goes and checks them digit by digit. So we took two textbooks, Jump Math and Skill Sharpeners, and we looked at their exercise sets, which required students to compare two numbers. And this is the graph that shows how the problems were increasing in difficulty level. So you can observe that the green progression actually moves on to more involved concepts very quickly. And it completely ignores a class of problems where the student is simply supposed to compare two numbers by looking at the number of digits. But this is something that the blue progression does. But the blue progression never reaches into more complicated traces at all. So this shows the different values that these two different progressions in existing textbooks actually offer. Now let me talk about another subject domain, and this time it's going to be a conceptual subject domain. And the idea that I will showcase here is something which I call template-based generalization. So consider this algebraic proof problem from high school mathematics. So the goal here is to prove that the left-hand side is equivalent to the right-hand side for all values of x. So this red problem is actually taken from a textbook, a very expensive one. But the teacher simply cannot copy and put this online. But now with our tool, the teacher can feed this problem to our tool, and our tool will generate problems that are similar to this one. So these green problems are hopefully not copyrighted and can be put online. or can be given to students for more practice if they want to practice this specific kind of problem more. So the way the technology works is that we generalize the red problem into a more abstract template, where we replace every operator by a whole that can be instantiated with an operator from that family. So for example, sec x is replaced by a whole T1 of x, where T1 stands for any trigonometric operator. Plus is replaced by a whole which can be filled in with either plus or minus. And now the challenge is to find all possible instantiations of this template that yield correct problems. So the strategy that we use is brute force search. We try out all possible instantiations of this template one by one to see whether the problem that we obtain is a correct one or not. But in order to test whether the problem is correct or not, if we were to use a solution generation technology like symbolic mathematics to be able to solve these problems, then this approach is not going to scale, because the number of instantiations of this template is several orders of powers of 10. And if it takes 1 second to solve one such problem, then it will not be real time to be able to generate these problems. But what we have is a technology that can quickly test whether the problem is correct or not. So it does not know how to solve this problem, but it can simply test whether the problem is correct or not by simply using random testing. So there's a theorem which says that if you were to randomly test these problems on random values of x, then if the two sides turn out to be equal, then with very high probability the problem is correct. So that's the technology that we actually used here. So it's a template-based generalization, and then we use brute force search to find all instantiations and then see which instantiations are actually correct problems. So in this case, our tool also ends up generating problems which are much simpler to solve, because if you look at the last two problems, they are true for any alpha and beta. Alpha plus beta times alpha minus beta equals alpha square minus beta square. So they are not really using the axioms of trigonometry. But then this is really an interactive tool where the teacher can say, oh, I don't like these problems because they are much simpler. Then our tool will generalize the orange template into more strict constraints, and then these problems will actually disappear. So this is a very general purpose technology. It works for several kinds of algebraic operators. So here you see this red limit problem, and if you feed this to our tool will generate problems which are very similar to this. And even though we don't have a proof of difficulty of the green problems, but it turns out that when we try to solve them by hand, most of them had similar levels of difficulty as the original red problem. Here's an integration problem. This is what our tool outputs. And this is another cool one. So this is joint work with Sriram Rajamani, who is a researcher at MSR Bangalore, and one of our interns, Rohit Singh. So now let me show you another application of this idea of generalizing a problem into a template and then finding instantiations of that template which are good problems. And this time from a very different subject area of language learning. So consider this sentence completion problems that are common on SAT exams, SAT exams. So the student is supposed to figure out the right word choice from a given set of words that will be a correct choice for the fill in the blank in the sentence. So both of these problems have one correct choice each from these 5 choices that you see. One of them is an original SAT problem, while the other one was automatically synthesized. So why don't you folks take a moment to stare at these problems and figure out what the right answer is? And would someone want to take a guess which problem was the one that was automatically synthesized and which one was the real one? So what is the correct answer for the first one? That's right. And for the second one? Yes, so second one is mercurial E. So the second one was the one that was automatically synthesized. And I really wanted to appreciate that there is not much difference between the similarity of these two problems with respect to their structure. So this is how the technology works. So very similar to the one that I showed you for algebra. So we take the original problem and we try to abstract it into a template. So the template for the original problem is someone characterized someone as dash because of dash. And then our teacher says, I want to find all instantiations of this template where maybe the fill in the blank is mercurial. So the new template now is someone characterized someone as mercurial because of dash. And now we have a regular expression-based query, which has some sophisticated language constraints as well. And we search the web for finding all instantiations of this particular template. And this is one of the sentences that pops up from our search on the web. So you can see that it is a very similar technology to that of the Algebra 1, but we are using a very different underlying backend to figure out whether it's a correct problem or not. So there we used some logical techniques. Here we are using the power of the web to figure out instantiations of the template. So now I'm going to illustrate one other final concept in something that can be used to automatically generate problems. And this is what I call symbolic methods. And the technology is can be seen as doing solution generation in reverse. So if we imagine we have a technology that can solve these problems, we are going to run that kind of technology in reverse to be able to generate these problems. So I will illustrate this using two other subject domains. So now I'm going to talk about logic. So where one of the problems that you see in this subject matter is that you're given some propositions like the red propositions, and the goal is to be able to prove the proposition on the right. And the way the student is supposed to prove the target proposition is by means of some rules which are called inference rules. So these inference rules tell us that if a student knows certain premises, then they can drive certain conclusion. And the student can also use replacement rules where a proposition can be replaced by an equivalent proposition. So this kind of course is quite common in introductory undergraduate curriculum, and several departments are required to be taking this particular course. So this is joint work with Professor Amay Karkare at IIT Kanpur and one of his students, Umair Ahmed. So now let me show you a demo of how this tool works to generate new problems. So we have three kinds of problem generation features here. So one kind of feature is what we call proposition replacement. So the teacher has entered a problem. So these are the premises, and the student is supposed to establish this conclusion by means of applying inference rules and replacement rules that I showed you earlier on the slide. So one problem generation interface that the teacher has is to be able to generate any one of these propositions, either a premise or the conclusion. So here I'm asking the tool to give me all replacements to premise 2. So the entire problem will stay the same except premise 2 will be replaced. And when I hit submit, then the tool finds me 455 different instantiations for premise 2. Right? So if I were to replace this second premise by any of these propositions that you see here, I get a valid problem. And each student now in the classroom can be given a different version of this problem, or every student in MOOC can get a different problem. But this technology still does not guarantee any kind of difficulty of the new problem that you will get by replacing those premises. So for that, we have a more sophisticated variant of problem generation. So we call this similar problems. So the goal of similar problems is to be able to generate problems whose proof structure is going to be exactly similar as the proof structure of the original problem. So in this case, the teacher simply needs to enter the problem, and when the teacher hits the submit button, then in this case, the teacher has found 177 problems which look quite different, but their proof structure is very similar to the proof structure of the original problem. And then finally, we have even more powerful tool that we can provide to the teacher, which is what we call parameterized problem generation. So here the teacher can say, I want a problem which has, let's say, 3 variables, 3 premises, maybe it has 2 abstract solution steps, and then these are the 2 key rules that the solution should be employing. And when the teacher hits submit, then the teacher finds 115 different problems that have this kind of feature that you see here. So this, I feel, is an extremely powerful tool in the hands of the teacher, where they can customize the difficulty level of the problem, as well as also select which concepts the student should be tested on. And the way the technology works is that first we ended up developing a tool that can solve these kinds of problems, so using AI techniques. And then we ran this tool in reverse. So starting from the conclusion, so we have some good guesses for the conclusion, and then we run this technology literally in reverse to be able to find some premises which will satisfy the features that the teacher wants. Right. So I showed you this similar problem generation, and the definition of similarity was that those problems whose proof structure is very similar to the proof structure of the original problem. And given a problem like this, our tool can output lots of similar problems. And this was really a powerful tool in the hands of teacher, where the teacher can tune various parameters and knobs, and then the teacher will get problems whose solution would have these kinds of features. Okay. So now I'm moving to the last instance that I wanted to impress upon you, which also falls in this definition of using symbolic methods and viewing the problem of, or the process of problem generation as solution generation in reverse. And this is the domain of board games. So suppose some child has learned how to play tic-tac-toe 3x3, so they have really mastered that game. So then game would appear very boring to them. But what if we had a technology which can help the student play some new games, some variants of these classic games? So in this case, for example, what about tic-tac-toe 4x4? And maybe I only allow the sequences that are row and column only, but not diagonals anymore. So it turns out that if you consider playing tic-tac-toe 4x4, it's even a more stupid game if you start from the empty board, because the person who plays first invariably actually wins if you want to make sequences of size 3. But if you start from some initial configuration of the board, then these games actually become very interesting. And this is what our technology allows us to do. So the person can say, define the rules of the game and feed it to our tool. And we also allow for what we call leveling the playing field. Because if an adult wants to play with a kid, tic-tac-toe 4x4 or 3x3, then it will be very boring for the adult, because the adult has much more expertise than the kid. But you can define the level of expertise of the kid and the adult, and then out will come some configurations which will be interesting for both the adult and the kid. And this is a joint work with Krishnendu Chatterjee, who is a professor at IST Austria, and one of his interns, Umair Ahmed. And the way this technology works is that we view the solution generation. We have a technology that can automatically solve such games, and we literally run this technology in reverse in order to be able to generate these interesting challenge problems for the student. So now I'll conclude. I really believe that lots of technologies that we have developed in the programming languages community in the area of program verification and program synthesis have a huge role to play in improving education. And by improving education, I really want to emphasize two aspects, which is to make the education more personalized and interactive. So in this talk, I focused on problem generation, automatically generating problems that might be tailored to a given student depending upon the expertise that they have demonstrated. But there are several other aspects of how technology can be used in making education more personalized and interactive. So first is that when you generate new problems, you should be able to automatically generate their sample solutions as well. Then when students try to solve those problems, you want to automatically generate feedback also. And Armando talked about some of these aspects in his talk. So if you want to learn more, you're welcome to take a look at this technical report, which you can pull up from my website, which goes into these topics in greater depth. And even though the emphasis that I personally have had on this area has been more from the direction of using formal methods and programming languages technologies, but I really feel that this is an interdisciplinary research area that can benefit a lot from other areas like natural language processing, because several problems are actually word problems. You do not simply start from logical formulations, but you have English descriptions of those problems. And also being able to take a data-driven approach at this, how you can use the data that you might collect by putting these systems online, and you can improve these tools in a virtuous cycle. So I'll conclude at that. Thanks for your attention.
Okay. So we're rounding this up with Zoran, who is going to show how he took some of Sumit's work and actually put it out there in the field. And he's going to share some interesting results. Let me make sure I get you set up. Plugged?
I think so.
There you go.
Okay. Before I get to where I really would like to get, I'm going to get you some background on where I came from. So really what I'm trying to do is create a new learning environment, basically that creates inspired learners and world-class experts. So that's sort of the top-level research objective that I set out to do. And if you look at sort of the standard approach, top level here, you kind of see this particular process. And it works for a lot of us in this room, but there's a huge percentage of kids and people around the world for which it just totally breaks down because the outcomes are not where we want them to be. So really, I was trying to see if there is a way in which we can actually usurp this entire process by adding another term in the objective function. So it's not just mastery, it's basically mastery with engagement. And then the question is, how can we actually have discoveries or knowledge come out of this process that's over and above what the standard educational process can do? And so how many of you have played or know about Folded, the game itself? Okay, maybe 1/5 of you. So basically, it's a game that tries to do protein folding, one of the hardest problems in biochemistry. If we knew the problem to this, we would know secret to life because we can synthesize new proteins. And proteins pretty much do everything in life, from digesting the food that you ate, to moving your muscles to where you just got, to defending against different viruses as you breathe in, etc. Okay.
Sorry.
Yeah.
I'll switch out. You got feedback.
Oh, okay. Maybe it's because this one is turned on as well.
Maybe. Sorry, we're having some problems. Try this one.
This one's on. Oh, is it turned on? Okay. So, does that work?
That's better. Yeah.
You can hear? Okay, good. So what happened is we created this game, and we said, well, let's see what people can do. And actually, in 2.5 years, it was not that people were able to make one discovery that was published in Nature, the most elite scientific journal, but actually 4 really big discoveries, 3 of them that appeared in Nature. So just to give you a point of one of them, there was a protein which was a particular strand of monkey HIV virus that people didn't know actually the structure of the protein. It has been now known for 13 years. Scientists have been working on it. They contacted us. We gave it to other players who developed their expertise solely through gameplay. And they solved it in 10 days. 2 weeks later, it was confirmed in the laboratory. So basically, something that 13 years people have been working on, we were able to sort of bootstrap in just 10 days with a number of different people doing things. Okay, so who are these people? We polled sort of the top 20 of those players, and you can basically see that 3/4 of them had one undergraduate course in chemistry or less. Okay, and I don't need to tell you how much you remember from one chemistry course undergraduate. And I can basically see there's only 2 of them that are professionally involved, and they're at the bottom of that top 20 list, I can tell you. All right, so that to me was the most exciting thing. These people did not know anything about proteomics prior to actually playing this game. So what that means is it's a new pathway to acquiring knowledge to some extent. So how do we do this? So here you basically see every notch on the x-axis is a new day, new data for new players for the particular day, and we basically measure sort of the ability of people to progress through a set of levels. They're optimized towards their ability to be best contributors towards some of these discoveries. So you can basically see every time there's a gap, a y-axis is a percentage of drop-off. So when there's a gap, there's basically we lose a lot of people there. So we had 80% people somewhere, and now we had only 60%. That's 20% people lost on that particular thing. So that's problematic. So basically what we did is on every 2 days, we modified the actual structure of the game towards optimizing this function on a daily basis. So we were fortunate enough, and even today we get like 200 to 400 brand new people every day. So every new day is a new experiment towards optimizing this function. And so we did this manually, and you can basically see this is 2 months here. We're able to sort of get almost a 20% uptake on just 2 months of optimizing this process. And so that sort of led to this whole way of thinking of this process as optimization of engagement and mastery. And when I started looking at how can I make an even bigger impact than just proteomics, right? You look at sort of the interest in STEM, and you see that in middle school, by the time I get them as PhD students, it's that tiny little infinitesimal sliver at the end, right? And how much could we possibly make a difference if this big drop-off can be averted in some way? So we started focusing on that early middle school. We looked at fractions that are key problems. We have now 4 different games that are basically fully adaptive and sort of optimized learning that have been tried. They've been played by over 6 million kids worldwide. This one in particular has been played by almost 4 million kids. It basically has kids learn the relative strength of proportions, but in a way that it's fairly irresistible for most kids. How many of you have played DragonBox? I've heard about DragonBox. All right. So this is an algebra game. So basically, you learn how to solve for x in a complex algebraic equation. This is how to isolate the box. Okay? So you start with just pictures, images, and cards. And here, for example, you learn that you need to divide by tomato, but then you have to divide by tomato on the other side of the equation too. And then you can cancel this and solve for x. Okay? And before you know it, this turns into real equations and real numbers. And you basically are able to have, and as you'll shortly find out, even kindergarten kids being able to solve for linear equations on a consistent basis. OK. So this game itself was developed by a Norwegian teacher, but we have provided an adaptive version of this game that's trying to maximize the ability of mastery for every particular grade. So really what we're trying to do is, and really the main reason why I went towards the games, is that they provide a way to do massive data gathering on optimized learning pathways in a way that the standard educational process, I would have impossible ways of actually finding that information. And just to show you, if you think, well, let's just use game knowledge and apply it to learning, here's basically a graph that shows how little is known, even for engagement in general. So here is a drop-off of players and the predicted sort of secondary reward effect, namely how much do these extra stars and coins matter when you try to play a game and collect them in addition. And people say, well, if we add coins, we're going to have some greater benefit, right? So the fewer people will drop off. In reality, if those stars are orthogonal to your main objective of the goal, you lose 40% of the people sooner. And this is a test over 6,000 people, complete random, blind randomized study. So it basically shows you how little is known about this process. Same thing for these badges and ranks that you see now. You can't help but not see them everywhere now. It turns out they help, but they have a very short-term lifespan. After a week at most, everybody just completely glazes over this thing and is no longer interested, partly because it's an externalized objective. So several different things that we've been doing is figuring out objective structures that will actually have kids self-identify with the actual process. So some of these games, you're actually creating an exam. So rather than you doing things, you're inverting the process for kids. And this exam is now given to the next classroom. So the kids are competing on actually creating, they need to know something in order to create interesting levels. And all these levels basically have to do with complex fractional reasoning. You can see there's a splitting operations on fractions. Here's another example. This is a 10th grader, way beyond mastering fractions, but he's still engaged in playing this game. How? Because his role is a role of an angel. What is he doing? He's basically seeing who in his school is currently in real time confused with a particular fraction. They have the question mark. And at that point, they're able to just put 2 circles in real time on the other kid's play. And if that circle ends up through data showing that this kid is more effective at understanding this concept later on, they get more angel points. So basically, they're incentivized to actually be peer tutors for younger students in the process. Okay, the other thing that I wanted to tell you, and so this is an analysis of how does adaptive process of specializing a particular fractional curriculum delivered through a game makes a difference in terms of some particular test results. And so the key thing to see is that there's a whole bunch of machine learning algorithms that are automatically tested against themselves. But one shocking thing to note is that here's an expert design progression that was later on verified. It's worse that the base case here is random assignment of these progressions. Right? So the expert, and this is what all our textbooks are written in, they all have great intentions. They all think about the key, most significant bits that to put in there. But the problem is too complex to actually manually design the right progression, even a static progression, let alone an adaptive one. So with that in mind, let me show you some of the adaptive courseware that we're building now. So we're building a 1st through 8th grade curriculum. Jump Math is a material that's in 15% of Canadian schools and is now making it into US school through Common Core. So the problems look like this. It's all paper textbooks. So the question is, how do we automatically or semi-automatically convert this kind of stuff into infinite progressions that adjust to every individual student? And so let's take an example of this. This is comparing 2 digits. It's a simple, very basic algorithm. It kind of the pseudocode kind of looks like this, right? So you keep comparing additional digits, and then you make your call. You can see that every one of those paths is labeled through these letters. So, for example, if we have the same number of digits and one has a greater number of digits, then you immediately know that one number is bigger than the other, right? So that's the path L. If it's the opposite, it's a path H. This is the path where they have the same number of digits, but the first digit is different and is greater, right? So you can basically see that I can encode each one of the particular problem sets as a sequence of these letters. There's an arbitrary number of these letters. So for example, any idea what is the code of these letters for comparing 313 with 324? OK, now you're all listening. Good. So it's DDS. It's 3 digits, so you're comparing them, and they're failing on the second digit, which is why it's just DDS. OK, so that's basically the trace. So you can think of every problem that you can generate as a trace. And as Sumit already depicted, what I like about this is it creates a general framework for analyzing all possible sort of problems that we can generate. So we can rank the difficulty, analyze and compare progressions, and synthesize new progressions. This is the key thing for us. So Sumit already shown this thing. I'm going to skip this. But suffice it to say that you can generate these kinds of progressions for any kind of problem. So you can basically see 2 curricula. One is green, one is blue. They're all optimal, but they're completely different. Experts writing them, so there's almost very little relationship between them. And this happens all over the place, right? So you can basically see for integer addition, the green curriculum really focusing on 2 concepts and switching back and forth from them, whereas the blue one actually expands onto some larger processes as well. And so we're basically have mapped this thing over almost the entire 6th grade curriculum, and we're going through the entire curriculum. And that's for procedural problems. Now, they're conceptual problems, so you can think of algebra, geometry, proofs, and I already talked to you a little bit about algebra. What I want to stress, though, is that the problems are enormous at some point. So basically, if you look at the space of all algebraic solutions that have, I think, 3 variables of less, and you map that space, it kind of starts looking like this. So this is automatically generated sort of possible set of concepts that you could be switching for just for that particular space, right? So imagine sort of asking an expert, all right, create some progression in this space, right? And you have, I think red ones are backtracing remediation steps, and the black ones are forward steps, right? So it very, very quickly becomes intractable. So as a result of this, you really need to have automated ways to reason about these things. So let me show you what we're doing with these automated systems. So imagine you have some kind of progression of concepts, right? And now you have sort of an evolutionary process where you basically have some set of operators that change this thing. So namely, here you're swapping these two progressions. Here you're introducing a concept before this bottom blue one. And then you have automatic ways of actually testing these things through reinforcement learning processes I'll just shortly describe to a huge number of kids. And you see that this one, based on some testing, ends up being sort of most conducive to kids' understanding. So this now becomes the next evolutive parent of the new things that we're exploring in this space. And we can do this not in a matter of years, which is what the standard educational studies are doing. We can do it in a matter of weeks. And that's the key reason that's really exciting. And that works not just for students, but also for teachers. We can now figure out what kind of data or what kind of actions should we present to teachers such that they optimally help the bottom 15% of their students as they're assessed currently, right? So the whole ecosystem can be optimized as opposed to just what can be presented to kids. So let me show you a little bit about how this works. So imagine you have a kid. This is their process of solving a problem. In this case, happens to be a game, but it could be anything. And so you know how they've done based on these smiley faces. And what you're trying to do is maximize student learning and engagement at the same time. So that's your sort of long-term goal. And the question is, what's the next set of problems we should present? And let's say we have one student going through this progression. We sort of say, oh, this person's doing pretty well towards the end. Let's see how well they do on a transfer. Imagine this is a test of ability to abstract knowledge. And they do really poorly. So that informs the information backwards. And now we have another student doing perhaps not as well, but they do relatively well on transfer. So this information propagates in both directions here. And so now, just with two students, for example, the optimal strategy is a path that has not been seen by a single student yet. Right? So this is the power of being able to sort of have a lot of these experiments and still inform for the optimal pathway. And this, of course, happens in the general instruction. We have many actions at every particular time. And you need to decide not just what is a single static progression, but how to adapt to each student. So here are the set of dimensions that we're varying in this space. Imagine each one of those letters as a concept. So if I have A and B, that means I have to solve a problem that requires me to know A and B concepts, to use concepts A and B together, right? So the dwell time is basically saying how long should I dwell on A before I introduce B. The concept layering basically says if somebody knows how to solve problems that require A, B, and C, and I have a D, when I introduce a D, do I just lump it together with what they already know? Or do I slowly recombine it with AD, BD, and CD, and then introduce it initially, right? So there's a whole space of scaffolding progressions here that is completely unknown and dependent for every student and every problem, right? So this is where this space is very large. And of course, concept ordering, something that's even if you look at Common Core, mathematical or English specification on what the kids should learn in K-12, it's a set of concepts with a loosely defined partial ordering. But there's no real microscopic level of ordering presented in that space. In addition, we're optimizing for hinting strategy, persistence and tenacity, long-term effect on domains, and self-identification. And let me just show you some of the interesting things. This was something we've done a while ago. But one of the standard progressions in games and learning in general is to sort of gradually lead people in this sort of zone of engagement, right? But here's what the optimal policy in this case. So the star is the level of difficulty, right? So basically, what the optimal strategy here ended up being is give the easiest level to everybody starting the game. And then 15% of those who do really well on that basic level, give them the hardest possible level you can give them. OK? And everybody does poorly on that one. and then you conclude with a progression on the first level, right? So nobody would design something like that with sort of the proximal zone of development strategies, right? It just would be a total no-no. You'd lose a lot of. But it turns out that for those people that do really well in the beginning, they need to be hooked on some really great challenge in the future that they see, right? And this is something that has been discovered through this exploration. And so this is another thing that basically points to that we cannot assume that some of the theories that we know in learning science will just generally apply to every particular problem. Okay. So here again, I can show you some of these things. So you can basically see that the static strategies versus the adaptive strategies are sort of somewhat subpar performing. You can see that the best static strategy, which is the strategy pulled out of the fixed strategy out of this adaptive one actually changes the strategy for every individual student, ends up performing that much. So the adaptively doing it for every kid, you can kind of roughly see has some. None of these numbers are very large. And this graph actually points to our way of actually analyzing the effectiveness of the algorithms without needing to experiment on kids to get that data ex post facto. So basically, we do this analysis offline, and then we present the best policy. This is joint work with Emma Brunskill, who I think is here maybe, or she's definitely, oh yeah, there. And so we're pushing this thing further and further. This problem is actually fairly hard, but if we could solve it in a general way, it would make huge implications. Okay, the last thing I want to tell you is something that just completed last month. So have any of you heard of the algebra challenge, Washington State Algebra Challenge? No? Well, we basically challenged the entire Washington State to try to solve I think we said 250,000 equations in 5 days. Okay, you see the outcome. In the end, they ended up doing 390,000 equations, and the kids are still playing. I can show. I want to show you some outcomes which are just fresh. You're the first ones seeing this data. Here's the shocking result of this adaptive strategy. So this is kids in different grades, and this is percentage of mastery for the entire classroom. Okay, so this is not just one isolated kid. This is all the kids. How many of them reached mastery, which basically meant the ability to solve a complex linear equation 3 times in a row without making any mistakes. Okay, and what you see is that we have average 93% mastery, including kindergarten, on solving for an unknown in a linear equation. After 5 days of play, of which all of these schools played roughly an hour and a half. So basically, everybody in the class played an hour and a half or longer. This is the results. If they played 45 minutes, which is roughly one class, this percentage drops to about 80%. So let me show you another thing. So this is levels of mastery. So you basically see each grade and how many levels kids play. This is an adaptive progression. You can basically see that you can play only about 60 levels and reach mastery if you just totally know the structure. But you can see that some kids in the kindergarten have played an order of magnitude more levels. And they've reached mastery. You can basically see also that as kids become older, then that thing narrows down. But here's the, yeah. So this is, I'm really excited. We're going to do this on the entire country of Norway in September. And I'm actually looking for additional states that we're going to be doing in September. And we're going to actually extend this thing to word problem solving. So then when you have a word problem, you have to model the equation and then solve it. And so it's not going to be kindergartners because they would have to read at that point. But I'm really excited about this new way of actually not only gathering data, but analyzing how adaptive structures work, and then basically using that information to have the next set of states benefit from that across the board. And so this same strategy is game here, but of course, we're going to have the entire 1st through 8th grade math curriculum based on the exactly same thing. So basically, as time progresses, every year the curriculum is going to become stronger and stronger because the data informs the best specialization for every unique kid. And I think with those, we can reach basically 95% mastery across basically math as it is expected to be taught by Common Core in K-12 really is like riding a bicycle. And I think that's perhaps one of the biggest goals that we're aiming towards, is that it shouldn't be so stigmatized as it is currently. And I think we have a way of changing that. So that's all I had to say. So thank you.
Wow. I have the extreme pleasure of presiding over a panel where every single speaker was on time. This is a unique experience for me. So I'm pleased to say we have plenty of time for questions and answers, or at least questions. So we have some folks here in the red shirts who have microphones, or will have microphones. Okay. So yeah, so just raise your hand and beckon them over. And who has a question?
I have a question for Zoran. Zoran, you showed an optimal pathway to mastering a concept. And I'm wondering if you could discuss a little bit the implications of that optimal pathway for what are traditionally considered multiple ways of learning. So if you sort of crowdsource what, I guess just a little bit more clarity on what does that mean for the other kids who don't reach mastery of that concept through that particular pathway?
Yeah, I mean, that's the whole, yeah, so the optimal pathway for every kid is a different one, right? So basically use the information about how the learner interacted in the past to figure out what the optimal pathway is for them, okay? So that's the ultimate goal, right? So basically the way that this is defined is there's an optimal pathway for sort of the middle ground, and then you have deviations of them. They're actually specializations for different learners in the process. And oftentimes, styles is something very controversial in learning science. It turns out that, everybody's visual, simply because we have way more neurons devoted to visual things than audio and tactile and other things. But there are many other things that for example, engagement, right? I have 3 daughters, and I know that they just, the way some of these things are presented, it just turns them off right away. So basically, let me just give you an example. We did a hinting study over 10,000 kids, where we actually presented a hint as sort of the basic, just do this and you'll succeed, something more abstract and even more abstract. And we expected that most abstract hints will lead to biggest learning gains, right? It turned out that all of them have completely negative effects on most kids. And the reason is that when you give unsolicited hints, kids feel like they've failed, okay? And this is something that nobody really considers, but it shows, it screams at it in data, and you're like, oh, I wasted this experiment for no reason. And then basically, if you change that such that they earn the hint that they elect to use wherever they want, you have completely different behavior happening, right? So there are all these other variables that don't have to do with the concept, mathematical concept, or but basically, how do I feel about myself? How do I see myself as a learner? Or do I already feel like that I'm not good at this, and as a result, every slight failure will make me quit, right? So all of these factors end up being way more important than what's the next math problem you're going to be presenting.
Hi, can you hear me? Dean Mohammed Ali from University College London. So I was really impressed by this work, and I can see that future reinforcements of this work will make significant contributions in education. I'd like to ask what your thoughts were on the use of cloud technologies to analyze the results and to feed back into the cycles of all of your projects.
Yeah, I guess we do this. I mean, really, as you can see, that I have a lot of experts working with me, and I love them all, but I don't trust any of them for the knowledge. So really the cloud and the data collection really informs me more than anything. So I just take everybody's theories and say, great, we can structure it in the process, and then we'll basically see what actually ends up being effective. And it's been sort of the right, for Foldit, we had to do that because there was just no way anybody was going to tell me how to get people to publish in Nature in 6 months, right? But even for education, it's shocking how little is known. And we have an opportunity now to really accelerate the ability to know not just how to assess kids, but really what is the next action. That's the key thing that I'm really interested in here, right? Because even teachers, you know, they don't care about looking at the analytics. They know that their kids are not understanding this stuff. They see it right away, right? What they need to know is, what should I do next with my next 10 minutes of class that will have the most effect? And that's something that we can discover.
Do you have a slide that has your contact information or something about this project?
Yeah, if you just look at, no, I don't have a slide. Do I?
Oh, at Jump Math.
It's.
So while he's getting that, are you?
So given the fact that this is actually for you as you're searching up there, you have the ability to discover new and more optimized learning pathways for a given student. And given that there's a lot of work going on in generating random or pseudo-random problems for them to solve, is there a way as the system improves itself, that you discover areas, sticky areas, where you essentially have to generate better examples, better problems, and you can somehow tell that from the way that people are maybe dwelling or some other metric?
No, yeah, that's exactly it. I mean, a lot of times, well, because, I mean, part of the power of the infinite courseware, as we call it, but it's really sort of underlying principles that Sumit has described. It allows us to sort of generate, think of every aspect of learning as a micro operational unit. So you can basically apply arbitrary queries. You can say, fit an arbitrary regular expression of a description of this problem. I wanted this problem to be a subtraction of 4-digit numbers of which I'm carrying twice, and the carries are on 2 digits that are 2 place values apart from each other, right? Give me a problem like that. And basically, there's a way in which you can automatically synthesize on that. So if you have that kind of powerful thing, now you can explore, okay, these set of problems that were given to kids, they're struggling on. What are the partial ordering? What are the simpler problems that directly descend from that problem, right? You're going to have 10 of them. Now you're going to use the data to figure out which one of those, if I scaffold kids through, will be most illuminating to kids towards solving this other problem, right? So the structure of being able to reason about the space of all problems allows you to use data to explore it, okay? And so before these automatic structures were in place, we had to rely on experts giving me a graph that's fixed graph. I can't add another edge. It's just there. And I can't create another problem. It's just whatever somebody has designed. And that's the key difference.
But the point of my question was that probably changes over time, right? You're never going to find the optimal path, right? You're going to continue to evolve. Well,
what you find is that you have sort of diminishing returns oftentimes, right? So basically, and that's how we're going to, when we have this curricula, you'll see basically in 3 or 4 years, I expect us to have huge gains. And you know, a lot of it depends on the curriculum, right? So you can basically say, this curriculum has a fixed point of 70% mastery, and that's it. So a lot of content providers are not going to like that, but we will actually have that information. They cannot be better than this, right? Whereas somebody is on a higher curve.
Hi, Becky Grinter, Georgia Tech. I wanted to ask whether any of the panelists had thoughts on, I mean, you all talked in some ways about how these technologies can reach more people create more learning opportunities. And so I wondered if you had any thoughts about diversity, about how you could particularly try to use these technologies to perhaps increase the number of minorities that get interested in science, technology, engineering, mathematics.
Well, I think there's certainly an opportunity here to use technology to make up for a lot of the shortcomings from funding and from crummy schools to actually be able to lift everybody to a common, to a level playing field, if you will. It's, I think that's probably the biggest impact that you can have with this kind of technology in terms of making up for the fact that some people don't have access to the level of teaching and the level of evaluation that other people have.
So I think this is really the goal that keeps me putting more energy and enthusiasm into this particular project of using technology to improve education. Because if you have classrooms where the teacher is very skilled and the student-teacher ratio is small, then these technologies might not add much value. But if you think about classrooms in developing countries where the teachers don't have great expertise, where the class size is big, then these tools can really empower teachers to be able to deliver more interactive lessons to their students. Another thing I wanted to add more in the context of someone asked how can cloud or data that can get collected on the cloud also help improve these technologies. So one question that I had for most of you who probably teach some courses, that would you be interested in developing these kinds of technologies for your own classes? Like how many of you here are thinking about putting up a MOOC course sometime? So it's probably like 5 to 10 hands. And have you thought about how would you make that environment more interactive? Because the normal classes that you are used to teaching, they have much smaller teacher-student ratio than what you will find on a MOOC. So have you thought about the role that technology can play in these classes? Okay. So one recipe that I have found useful is that there's a kind of a chicken and egg problem in developing these technologies which will work great versus attracting more students to be able to use these technologies. So one recipe that worked very well in the work with Armando was that if there is some platform set up that can even provide even tiny bit of value to students using that, studying in that course, then you get the process of collecting data started. And once you have a lot of data, then you can start thinking about what kind of feedback technologies can you build. So some of the things that I talked about, like problem generation, maybe there is some progress that you can make in that area without data. But especially in the case of feedback generation, you really need to look at what kinds of mistakes are students making. And this is also the place where the kinds of mistakes that you will see will also depend upon classrooms to classrooms. So once the data is collected, then we start looking at what kind of feedback mechanism tools you can develop, and then the virtuous cycle actually starts kicking in. So I would really encourage you folks to switch on to a medium where all the different exercise sets that you give to your students and the solution that the students submit back actually you start to digitize them. And then find someone at your university who has the expertise or who would want to do research in this area, or contact us to see if we have some tools that we can provide you, or some general ideas that we can collaborate together to develop such tools.
So one thing also that I'd like to add to that, so MOOCs are a very obvious application for this kind of technology, but they're by far not the only one. And even in the traditional classroom, you actually have even a lot more opportunities for deploying technology that might not be fully automated, but that in conjunction with skilled TAs and skilled instructions can actually make a big difference. And just because you're doing it in the context of a traditional classroom doesn't mean that you cannot collect data, and it doesn't mean that you cannot do a lot of these interesting analysis. The scale will be different, but the depth of insights and knowledge that you can gain can make up for that in some cases. So there are some questions.
Well, we're unfortunately at the end of our time here. So I know there's lots of questions. I encourage everybody to reach out to our speakers and to grab them in the hallways. They'll be around, some of them, for some time. And you know, talk to these folks and we can work together. So I'd like to thank our speakers one last time for coming today. And enjoy the break.